Hello, everybody. I don't know if my mic's working, but if it is, we will be getting started shortly. I would put on a camera so you could see my face, but this is a brand new computer that has no webcam yet, so I am a gray icon. Okay, yeah, we'll be starting at 7:02, so just about a minute from now.
All right, so I think we're about to start. So yeah, I'm going to be starting. I'm Ryan Asmolater. I'm going to be presenting this Learning Adversarial AI with Checkers workshop. So before we start, I just want to make abundantly clear, if you have questions, please do not hesitate to note that in the chat. I will get to that, and I want to actually give you the answer, because I mean, what's the point of the workshop if you guys don't learn? So anyway, let's get started. There we go. So I already said who I am. I'm Ryan Aspenlater. I am a project coordinator here at AIS at UTD, and I'm going to be presenting this workshop. So here's our agenda. If it's okay if you don't know what most of this is or any of it is. We will get to it all, and by the end, hopefully, you will at least be acquainted a bit with some of these terms. But we'll have covered all this in a relatively short time. So again, if you do have any questions about any of this, please don't hesitate to ask. So before we get too deep into this, I just want to clarify some terminology real quick. So whenever I picture one of these two pieces on the left here, those are pawns, and those are just any piece that's on a king. And on this side, these are the kings. So just checker pieces that can move in all four diagonals as opposed to just two of them. There's also a term that's going to show up a bit called a search tree. Now, what a search tree is basically, it's just a tree that's going to be searched through by the algorithms we end up implementing. But there's just the root node, which is the top node, which is where you start from. And then there's these terminal nodes, or nodes where there's nothing coming from them. So I just want to get that out of the way. But again, any questions, feel free to ask. So first of all, what is adversarial AI? Well, it's a relatively simple concept. Basically, in adversarial AI, two AI agents compete with each other, and they make moves based on how they think the other will react. So that's the main idea. We're trying to leverage how our opponent will act in the most optimal way, so we can act in the most optimal way. So first, we'll get into checkers a little bit to see just what kind of concepts you can take from that into AI. So Checkers is what's called a perfect information game. It's basically a game where all information about it is known, and if you had enough resources, you could compute the perfect strategy. And I'll get to that later, but that's theoretically possible for any perfect information game. It's also played on an 8x8 grid, but only 32 of the pieces are ever 32 of the positions are ever really used. And then at any time, a player must capture a piece if he or she can, and multiple pieces can be captured per turn. The game can end in a number of ways, the most common of which is a player loses all of his or her pieces, but it can also end if a player can't make a move, and the rare case, 40 moves have passed where no piece was taken. So there's similar things that occur in something like chess, where it forces a stalemate after a long enough time. So now we can get into the actual adversarial AI. So we're going to start with something that's relatively simple, but also extremely fundamental to adversarial AI, and that's something called an evaluation function. Now, basically, they answer the question of how do we know if we are actually winning? Someone like actually knows how to play checkers, for instance, will probably have a good idea of whether they're winning or not in any given state. But a computer doesn't have that knowledge. So what we have to do is take our understanding of checkers and basically translate that into a function or an equation based on that. Basically, it will give us a score. If a score for an evaluation function is 0, then the game is effectively tied. But if there's one side that's higher, that has like a really low negative value or a really high positive value, then that side is winning. And so for a lot of these, I'm going to have it where white is going to be, if white is winning, that'll be designated by a positive value, while black is designated as a negative value. And the greater the magnitude, the greater the winning. That's what we're trying to do. But that actual function can be difficult to figure out without an understanding of how the game works. But there are different levels to this. So the easiest type of thing would be something like a simple evaluation function, like what I have listed. So for instance, generally speaking, if you have more pieces than your opponent, you are winning. That basically almost always true. So you can have something like this, where it just takes the difference between the white pawns and the black pawns. And then kings are a bit better than pawns because they can actually move a bit. There's a bit more fluidity in how they can move, so they get more options, so they're worth a bit more. And so we had a multiplier for the kings. Now what this function will do is then you can just apply it to a board very quickly and determine a very quick numerical result stating whether we are winning or losing on that board. We can obviously do more complicated functions than this. Like they can take advantage of some additional information. For instance, where is each piece on the board? If a piece has the option to make more moves, it's probably a better piece. It's probably a better position for that piece. Also, what stage of the game we're at. So, like, if we're in the late game, we're going to try to prioritize taking out the last few pieces. While in the early game, we might try to prioritize getting pawns to kings. And then lastly, if we need to prevent some kind of stall tie, because there's a chance with the current functions we have that a algorithm might never actually attempt to engage with the enemy and just happen to tie, even though that team might be winning. So, as a quick example, here's a chessboard. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are actually 9 white pieces. So I actually messed up the value here. But there are 9 white pieces, as well as 1, 2, 3, 4, 5, 6, 7 black pieces. So, actually, I didn't mess up. That's great. So, because there are 8 white pawns and 7 black pawns, then the pawn value is going to have a 1. Well, since there is 1 white king and 0 black kings, that'll add an additional 1.4 to the score. So the actual evaluation score would be a 2.4 for this particular board, which would show a clear lead for white. So this is a position where the white player really wants to get to, and the black player is going to try to avoid if all possible. So before I go any further, does anyone have any questions about an evaluation functions and etc.? just give it a few more seconds because I know it can be a bit of latency. Going once, going twice, sold. All right, so I guess we can move on then to probably the most important algorithm that we'll be going over. So next, we'll be talking about the Minimax algorithm. This is something that's going to be at the heart of anything we do in adversarial AI. But don't be intimidated by this. Basically, what Minimax is, you want to, one player always tries to maximize their evaluation function while the other wants to minimize it. It's a zero-sum game. So a highly negative score would mean black is winning. That is, in this specific evaluation function, absolutely yes. Black would want negative and therefore would want to minimize the score as much as possible, since a really low negative value would indicate a very minimal value. And I'll be getting into that in a minute, but basically, if there's the maximizing player's turn, so if it's white's turn in our case, they want to choose the move that guarantees the highest value of evaluation functions regardless of what black ends up doing. And black wants to do the opposite. They want to choose the move that guarantees the lowest value of the evaluation function regardless of what white does. So that's where Minimax comes in. And to kind of illustrate that a bit more clearly, I've illustrated a search tree. This is a very simplified tree because there are a lot of additional moves that could be happening, but I removed them for the sake of fitting it onto a slide and not overcomplicating things. So we start at this position up here, the top position. It's black to move, and I show two of black's possible moves. It can either push a checker right here from this position to this position, or on the right side, it can move its checker to block a potential capture. And then there's a few results of what could happen are down here. So the first step for the Minimax algorithm is to go to the terminal nodes, these nodes right here, and evaluate them using our evaluation function. So let's go through these one by one. So at the beginning, this is really early in the game, so there's actually, both sides have the exact same number of pawns. So as we go down to the left, we actually see that white has captured a piece. So based on our current evaluation function, the score is actually 1 because white has a 1 pawn lead. Now these other two terminal nodes, the ones in the middle and the one on the right, no pieces have been taken at all. So these would have an evaluation function of 0. So it just keeps track of that. Then we go back up the tree. So we start on this, we go into the second layer. Now it is white to move. So they're going to try to maximize the possible value they get. So in this case, it's actually pretty trivial. In this case, they only have one option and it's a 1 point. So they're going to get 1 point. If from this board over here on the right side, they're trying to get the maximum of 0 and 0, which is 0. And then we go up again. Now it's black to move. So black's trying to minimize. And the minimum between 1 and 0 is 0. So 0. And lastly, we just have to backtrack a little bit to get the optimal move. Now, because we found that the right side, this right move is the move that results in a lower value for black, it should take that one when given the two choices. So this is the optimal move. Does that example make sense to everybody? Or do you have any questions about this example? How do you know if the function is correct? That's something that actually kind of comes from the most clear way of telling if the function is correct is just testing a bunch of different functions on Minimax and seeing which one ends up actually performing the best. But you can also use some intuition. There's actually a little issue with our function right here in that it's pretty obvious that black's going to take this pawn in the bottom left corner. as soon as the next move. That's actually an issue with Minimax that I'll be getting into in a minute, but that's basically the idea of something called the horizon effect, which I'll get into later in this presentation. In that, it basically means that you're not looking particularly far. You're not looking far enough ahead, and you might not notice a capture right at the end of its search. Wouldn't this hill climbing not necessarily be the most effective? So there's a couple of ways of doing this. This is the unoptimized version of. This is actually a slightly. I did kind of say this a bit differently than I should have, but basically, what happens is Minimax is what's called a recursive function. Basically, what that means is that it's a function which calls itself to some extent with some smaller set of values. So what it does, Minimax would be called on the board it's currently on, which in this case would be the top. And then from there, it would basically call it on its children nodes, which are these two middle nodes, which would then be called on the bottom nodes. Now, it just wouldn't actually do the scoring until these evaluation functions down here are called. Does that clear things up? All right, I'll go on to the next. I am a bit confused. Isn't the optimal move the one on the left, since white wants to maximize its score? Just to clarify, this is black to move right here. So black is going to try to minimize the score. If it was white doing this, then white would definitely pick the other move. I thought adversarial networks are for image processing. That's kind of a different situation. This actually has nothing to do with machine learning, because in this case, everything is coded, basically, the intelligence is actually coded explicitly, as opposed to machine learning where it isn't. Basically, it's usually involves some level of neural networks, which will basically find a optimal result after a bit of some amount of randomness, some amount of optimization. But adversarial networks, they are in machine learning. They are used for image processing. This is a separate process. Does that clear things up for you? Like, this is Minimax, and adversarial learning is that concept. Okay. Is it possible to have a situation where white might choose a different evaluation function from black, or one eval function always be guaranteed to be better than the other? That's an interesting question. So my guess is that there would technically be a best evaluation function, but it might be extremely difficult to find. Like, as I mentioned before, this is all based on a very simple evaluation function, which is just, it's for the ease of computational speed and all of that, and just for the sake of showing you. But you can do much better. As I mentioned, you can do more complicated functions that might be more effective. It is possible to have a situation where might choose a different evaluation function from black. Okay, I'm sorry. There's something I should clarify first. I'm taking this from the assumption that we're choosing from black's point of view. Black only ever uses one evaluation function from its point of view, and it assumes white is also using that evaluation function because it thinks that evaluation function is what optimal behavior is. So it's going to assume that white is doing the most optimal moves it can, so it can retaliate. It is possible from white's perspective that it's using a different evaluation function, and it'd be interesting to see two different evaluation functions compete, because then you can kind of determine which one might be the better one. But does that answer your question? Do we go into more complex evaluation functions later if we're looking further ahead? So looking further ahead is a bit separate from an evaluation function. All an evaluation function does is when you get to the terminal node, which I'll get into in a minute, it's just you take all the game information that you have and you compress that into one very specific number that determines how well you're doing. That's all the evaluation function does. The Minimax and its depth search, which I'll get into more in a minute, is what determines like the depth and looking further ahead. Does that clarify things? why do we start with the terminal node? So the reason we would, for scoring. So are you thinking of like attempting to call the evaluation function on other nodes? If that's the case, that kind of, what we're trying to do with Minimax here is we go to the terminal nodes. The reason we do that is because we actually have, then the follow-up boards, they're only dependent on, okay, I'm sorry, I should go back and explain that a bit more thoroughly. What we're trying to do with an evaluation function is determine how close we are to winning effectively. The higher up these scores are, like if we were trying to evaluate like this board right here at the middle top, it doesn't really do much for us. Like that doesn't tell us more. It doesn't really tell us about how we should proceed. What evaluating the terminal nodes does is that allows us to basically, we get information from there. Then what the opponent will try to counteract by taking the move that benefits it the most. And that is a more accurate representation of that board because that's what the other player will allow to happen in the worst case. And so on and so forth. Does that clarify things? It's okay if you don't fully understand this. It might be kind of weird to visualize at first, but I'm just gonna wait for a little bit more. Are there any additional comments about this? So 5, 4, 3, 2, 1, elephant. Okay, so from here, let's just explain a little bit more about Minimax. So the theoretical version of Minimax goes all the way until the end positions of the board are reached. So basically, reach positions where the game is ended. Now, for basically any game, that's completely crazy considering the number of boards that are possible. But basically, we go into the terminal nodes. Each of those are evaluated. Then we backtrack, as I showed before, and then choosing the lowest child value if it's the minimizing player's turn, and vice versa for the maximizing player's turn. But as I said, there are some problems with that. So Minimax is, if it's allowed to go in its entirety, it is a perfect algorithm in that it will always make the best possible move. But there's a big caveat there, and that's to make it perfect, it would have to look at every single position that is possible in any game. And for even the really basic games, that is way too much. Like, for instance, checkers has more than 50 quintillion possible board states. That is a lot. And it would take far too long to actually make a function that go through all that. Heck, it's kind of hard to do it for even shorter depths. So making it go all the way to the end is kind of a bit crazy. Something like chess is way more complicated. You can have as many. It's been estimated because it hasn't even been determined what the upper bound is, but it's estimated to have more than 10 to the 44 possible board states. Kind of a really crazy number that's not even within no hope of ever reaching that. So we have to actually decide on a depth to search to. And then from there, it becomes an issue of what search depth we are allowed to go to, because the runtime of Minimax exponentially increases as search depth increases. So for instance, let me go back to the slide I skipped. So this is a different, more complicated version. Isn't Tic-Tac-Toe super easy? That one is pretty easy, and I'll get into that later, because that's a very simple game. So that one is simple, and that one you could solve perfectly. That actually is something called a solved game, and I'll talk about that later on. So anyway, this is a more complicated search tree, where basically the boards have actually been, this is just a more generic piece, but basically it's simplified so that it's just the evaluation function and no board, because that's kind of the goal of an evaluation function. So we go all the way to the bottom. These bottom things are the terminal nodes, and this is just a more generic version of the thing. So basically, so on the bottom layer, you evaluate, is Connect 4 a solved game? That I don't know. I'm curious if it is. I wouldn't be surprised if it was, but I don't know. If you research it, it'll probably be available. But anywho, the minimizing layer, it'll try to choose the minimum possible value. So for instance, it'll take 10 in this case, as opposed to positive infinity, which would likely imply that the white has 1. If it's an infinite, that's usually meant to show that one side has 1 and the game is over, because they can't have a better position than that. Then 5 becomes 5, -10, -10, and so on and so forth. This keeps going. But this is a demonstration of Minimax at a bit of a deeper search step. Now, this can balloon and become pretty complicated to actually visualize, but a computer can handle it to a higher extent than we can. So we already mentioned the problem with Minimax. So that's where alpha-beta pruning comes in. Now, what alpha-beta pruning is, it's basically a technique that you can augment Minimax with to make it run way faster. It is something that is super beneficial to making Minimax actually work for depths that are a bit deeper than you would be able to feasibly do otherwise. So basically, the whole idea of alpha-beta pruning is that we don't have to check board states that would never be reached by an opponent if they could let it happen. So there's values of alpha and beta for each board position, where alpha is the minimum score that the maximizing player is assured, and beta is the maximum score that the minimum player is assured. And in the best case, this can cut the power of Minimax's exponential growth in half. So that effectively means that in the long term, at least, alpha-beta pruning will basically run for, in the best case, it can run twice as deep as Minimax, which is a big deal. So it's a little weird to understand at first, so I'll get into a minute. But basically, here's a kind of a demonstration of what alpha-beta pruning is like. So we have our game tree here, and we have these evaluation functions. So I guess we can, as I mentioned before, the Minimax function is actually a recursive function. So basically, it calls itself to make two smaller functions. So for instance, we start on the max, we call it, and it basically calls it for each of its child nodes, which each call its own child nodes, and so on and so forth until we reach this terminal depth. Now, what's interesting about what alpha-beta effectively does, and you'll see this first if we're evaluating from left to right, we start right here, in this bottom layer right here. We go to 7. We have a value of 7 for the evaluation function. Then for this next child, we have an evaluation function of 4. Now, because this is the minimizer trying to figure out the lowest possible board, it then looks at 5. Now, because it's a 5, it's higher than something that's already been found. We can just ignore it in any child nodes it has completely. It can be ignored in its entirety. Now, it doesn't mean that much in this particular case, but if we went all the way to the far right, we would see a bit of a better example. So we'll get to, with the recurrent function, we'd start at 6, go to 5, and then it would run its function. So first of all, we'd go to here. We'd go to this bottom square right here. The evaluation function would have a 5. The minimum of 5 is 5. The maximum of 5 is 5. Now, if we went over here and tried to get basically 8 from this, we get the minimum value of 9 and 8 is 8. Minimum value of 6 is 6. The maximum of 8 and 6 is 8, which is lower than anything else. That 8 is actually higher than anything than 5, so we can disregard it. Now, I understand it's a little weird to see on here. I didn't do the greatest job of actually visualizing it. But what this effectively does is if we decide to evaluate things in the right order, we can cut off a lot of extra computation off of this. And we can ignore a lot of moves that would never be reached. So, sorry, I kind of rushed that a little bit, but do you have any questions about alpha beta pruning? All right. 5, 4, 3, 2. Oh, there we go. Can you point out the optimal path here? Sure. So you can use this as an example. So, okay, I'll get to the next question in a minute. First, let's go with the optimal path. So this has already been evaluated, so I'll just skip that step. So the value of the node is 6. So because we're the maximizing player, we're trying to get the maximum possible value here, which in this case is 6, the maximum. So these I don't have the boards on here, but whatever position this refers to, this middle 6 right here, that would be the move that would be optimal. And then we can continue going down. It's kind of weird because then it'd be the minimizing player's turn who would want to do something that would be their optimal would be something that's different from the other optimal. So it's a little confusing, but in the short term, it's this move right here that'd be the most optimal. What about chess sacrifices? So that's something that I understand, like we're not talking about chess right now, but like the idea that you can give up a piece in the short term to make your position better in the long term. That's something that comes from searching at a deeper depth. That's part of the reason that we actually search at the terminal level, like the lowest possible level first for evaluating functions. Because if sacrificing a certain piece, let's say, guarantees that eventually we'll have a better position, then this would account for that. As long as the search depth is deep enough, which is a bit annoying. But generally speaking, the deeper the search, the smarter the agent is, and if the depth happened to be infinity, then it is a perfect agent. Of course, that also means it's a lot slower. So there's a sacrifice there. Does that answer your question? All right. I'll give another 15 seconds or so, and then I'll move on. Alrighty then. So if there are no more questions, again, if you do still have questions, so ignore it for the most part. I'm not sure what you mean by ignore it for the most part. I guess what you mean is that you don't actually evaluate the boards that aren't at the bottom of the tree. They're not evaluated using the evaluation function. The only reason we get those is we actually just get the maximum or minimum of everything that's below it. And the only time we ever actually evaluate something is at the very bottom of the search tree. So the board actually isn't really determined. Regardless of how bad or good the board is, it's not actually really read because what matters is what comes after it. Does that clarify things? I thought you figure out the optimal path from the terminal node, though. So I'm trying to think what you mean by that. So it's not really a path. We're only trying to get this first move because things can escalate and change to an extent. But basically, we do all this. We work from the bottom and work our way up after the recursion's been done and all that. And then from there, we have the information to determine what is the maximum or minimum possible move, which in this case would be the middle. So the only part of the path that's really relevant is this middle part right here. Does that clarify things? Again, this is a pretty important, so it's okay if you have any questions. I'm free to stop for a bit so we can answer any of those questions and make sure that we have some amount of understanding. So if no one has any additional questions in, say, 20 seconds, I'll move on if that's okay. Okay, so I guess we'll move on. So just something to preface before I go forward is that all the improvements to the algorithm that I'm mentioning right now, generally speaking, won't have as much of an effect as alpha beta pruning. So I'll be running through them rather quickly because alpha beta pruning has by far the greatest effect as opposed to all of these on the speed at which something runs. Just to clarify, all of these changes besides the last one that I'm going to be mentioning won't actually affect which move is chosen. The only thing it would affect is the speed at which it's reached. The only thing that would actually affect which move is chosen would be the search depth and the evaluation functions. So moving on to move ordering. This is pretty simple. As I mentioned before, alpha beta pruning, when the order of the moves is optimal, will basically reduce the power of exponential growth by half. However, we have to actually reach that reach the right order in order to maximize this. So what we're trying to do is evaluate really good moves early on, so that way we could potentially skip a lot of other moves. And there's a number of ways to do this. This can vary for a lot of games, but one option that works for chess is to evaluate moves that can force a capture, because this can involve a lot of quick movement and involve extra piece transfer that can happen. And it can potentially result in particularly good or particularly bad moves. And so we can evaluate those first, and that'll give us a better shot at skimming off extra things that we can ignore later. It's a pretty simple concept. So next quick thing is transposition tables. So a transposition table, if you don't know what a hash table is, it's basically what we're trying to do here is basically make a data structure where it keeps track of all positions that have been previously evaluated during this run of the function. And from there, it'll basically, that way it can keep track of the scores of those positions. So that way, if the position would show up multiple times in the tree, which can happen in the case of there's two different sequences of moves that reach the same overall position, that way we actually don't need to evaluate it more than once or twice or how many times it shows up. So this can save some time depending on the structure of the board and how the game works. So to do this, we have to store the state of the board in a relatively small number of, try to store this, remember, as we're trying to get basically get a value that represents the game in its entirety at that position. So in checkers, one way this could be done is to have a board that could be stored as like a 32 character string where the nth string refers to the nth position on the board. And this is a really simple version. This isn't necessarily optimal. This is just to illustrate the idea. But basically you could have 0 be that for that position to have no piece on it, 1 for a white pawn, 2 for black pawn, and so on and so forth. It should also probably have an additional value to say whether it's white's turn or black's turn. And lastly, this is the thing that actually would affect, that might affect the move actually selected. This is something called Kinesin Search. I might have butchered the pronunciation, but you'll forgive me, right? Anywho, so this is basically addressing the problem that we mentioned earlier. So if you remember, I said something called the horizon effect. That's basically the idea where regardless of how far you evaluate, if you choose a fixed depth to search to, there's always the chance that you get to a position that's actually really bad the next move and the next move, but you can't tell. For instance, one example of this in checkers would be doing a bunch of searching, and in that last position, you just get to a really good position, but the next move, your opponent can do something back that's really bad that basically resets everything. That would be a case of the horizon effect. And we can't really solve this with a fixed depth search. So that's where Kinesin Search comes in. So basically with this, once we search as deep as we can, we look at each of those terminal nodes and we check to see if that position is stable or not. It's often referred to as if it's quiet or noisy. So if the position is noisy or unstable, or basically a position that a lot can happen quickly and change, an unstable position, then we want to keep evaluating until we reach nodes that are stable, or basically positions that won't change quickly in terms of how good or bad they are for a player. So for checkers, one good example could be of an unstable position could be a position where a piece can be taken immediately, because the state of the board will change pretty quickly at that point. And it would solve cases where, the case I mentioned earlier, where placing a piece in front of another, and then the next position that we can't actually evaluate yet, the opponent would take the pawn. So this is kind of a visualization. Excuse the image quality, but this is what I could find. Basically, we search up to a certain depth, this flat line, this search depth right here, and then we look at these nodes and determine whether they should be continued or not. So for instance, in this far left one, we looked at it. Based on this, it is unstable. So we have to actually continue evaluating further until it's just stable nodes, and we can stop at that point. And as you can see, there's not too many positions where this is actually the case. So we don't actually waste too much time here in most games. So this is a way that we can try to mitigate the effect, though this works better on certain games than others, and it takes some amount of experimentation. So I know I went through a few different optimizations really quickly. They're a little less important, so I didn't give it as much time for them. I can answer a couple questions about them before I go forward. I'll give maybe a minute for people to ask some of the questions, and at that point, I'll move on. You can also ask about earlier concepts if you'd like, if you just thought of something. It's not like we're restricted to these things. All right, I'll give it 10 more seconds. Alrighty, so I will move on. There's not a whole lot more to talk about. So next we're going to talk about some solved games and a certain thing called Chinook. Now, we briefly touched on solved games before, but basically a solved game is a game where a definitive optimal strategy, I think the end of the one. Can you clarify what you mean by that? Antema, could you reiterate? Oh, okay. It's okay. This will be posted on YouTube later, so if you want to see the rest of this, feel free. But continuing, solved games. Basically, a solved game is a game where a definitive optimal strategy is discovered. So if you chose this optimal strategy, it'd be the best possible case. You would know for certain whether a certain player can force a win or not. And one of those solved games is something called Tic-Tac-Toe, where neither player can force a win if they're both playing optimally. And because of the numbers I mentioned earlier, it's very rare to have a game to be solved at all. But checkers has been solved. It actually was solved in about 2007 by the Chinook project, where basically checkers was solved in that two perfect players can guarantee a draw. And using this information, there was a agent developed called Chinook, which basically implements this optimal strategy. And because of that, it's actually 100% impossible to beat Chinook and checkers. And if you pitted them both against each other, the best you could possibly do is force a tie. But it'll usually beat you. But it's just kind of to show that these kind of games still can be solved. It's just a much bigger ordeal. This took nearly 2 decades of work. And this is something like checkers. If we go back and see the number comparison real quick. Sorry, I think I jumped it a bit. But the game of checkers has about 50 quintillion possible board states. And the reason we know an exact number is because actually all those states were found. Now, we can look at chess, which has orders of magnitude more. So unless we have a dramatic jump in computational power, that will be effectively impossible. But something like checkers is doable. I'm pretty sure that you can beat Tic-Tac-Toe, but only if you play first. Could you explain for me? And there is a chance there is a decent chance I'm wrong on this, but I am relatively sure that you can force a tie on either side. No, we'll get into. If you want to say more, you can just explain that. In the meantime, I'll go on to the code. So I have a link here to go to basically a Google Collab notebook that I created to help illustrate some of these concepts on checkers. Yeah, okay. It ultimately ends in a draw. So anyway, I'm going to move on to the code now. I'll jump over that really quickly, and then I can answer some last-minute questions. So now we've reached the code. So if you want the link, that will be, again, this is going to be on YouTube, so you can always go back. This should be publicly accessible, but if it's not, you can say somewhere in the Discord. You have to have 3 corners. Well, not really, because by doing that, the opponent can basically move in a way that can force you to respond quickly enough. If the second player doesn't know how to play, but it has to be. We're assuming optimal play here. If both sides are playing optimally, then the best that can happen is a tie. But obviously, if someone is not being particularly smart, then the other side can win. That's what's meant by a solved game. Does that help? Anyway, I'm sorry. I'll go on to the code. So this is basically I split this up into a number of different sections. So there's the checker setup, which isn't especially important to get into, but basically this sets up all of the classes and functions necessary to actually do anything. You'll notice with a lot of these kind of implementations that it's important to, thank you for posting the link. If you don't, the kind of most annoying part of any kind of coding for this is just figuring out the setup for the actual game itself, because the actual algorithms aren't too complicated. So I'm going to skip over this for now, because you can kind of look for these at your own pace. I have this commented out pretty well, so if you have any questions, those should hopefully fix anything. So we have our evaluation function. This is the same thing we went over in the call, except I added a couple extra things. Basically, if we reach a point where white has 1, then you return a value that is effectively infinity, 9,999. And if black wins, they return an extremely low negative value, basically negative infinity. And then if there's no winner or there's a tie, then in this particular case, we don't actually incentivize the players to reach that point. So we actually have a slight negative or slight positive value. So unless they're losing by a lot, they're never going to go for a tie. Though they might still, depending on the depth search. Then there's Minimax, which if you look through this and look, it's not actually particularly complicated. It's you run Minimax. If we're at a terminal node, you evaluate it. Otherwise, you expand it. If you're on the maximizing player, get the maximum via recursion. Otherwise, get the minimum via recursion. And then alpha beta pruning is 100% identical, with the exception of keeping track of alpha and beta. And it if we reach certain points, it'll actually just break off and not evaluate the remainder of the function. From there, I also have testing, where basically we can see how we can kind of see how some games would work. I'm gonna just run this particular one because this one runs pretty quickly, where it's a random AI versus AI that's using alpha beta to a depth of 4. Hang on, I've got to connect real quick because I forgot I actually have to run these things. So bear with me for a minute. Again, if you want to ever look at this, you can go there yourself using the link that's been posted already. Or if you missed that, it's on the chat. Or if you're watching the recording, I sent this a few minutes ago. So running these things real quick. Then we can watch this play. And it's not the greatest graphics, but that's what works on Google Colab. So basically all these moves happen. And this can take a bit, but white is practically guaranteed to win this because it is not, black is playing randomly and white is playing with some level of intelligence granted by alpha beta. So I'm going to go back to this in a minute. So I have a couple additional tests where you're pitting against teams that actually players that have different search depths. Right here, there's actually a time check. Comparison to C, ignore this. This isn't the case anymore. But basically, this is. I'll get to that in a minute. But basically, there's a thing here which basically will calculate how long it takes to search at a particular depth at particular plays. So do you just keep clicking all the play buttons? So this is actually something that I coded in the past. The way Google Colab works, it's kind of interesting. I'm going to go back up. Basically, you can create code blocks and text blocks. If I put a text block, for instance, it makes text block. And it's pretty simple. It's just regular text along with a little bit of markup if you want to make it fancy. But it's just text. There are also code blocks. Oh, you see here, white 1 and not even close. There's like 6. There's like white has 6 pieces. Now, code block you can add. This is where you could actually add code. And for this, it's Python, the programming language Python. So basically, you would do whatever code you want. And then what you can do, what's kind of cool about Google Colab is that you can actually run like specific pieces of code. And like you could run, for instance, all the code here by just hitting the play on each of these. And then when it's bunched up like this, you can actually just hit play and it'll run all of them. But that's the main idea. I'm not going to go over how to program in all through Python right now because that's a bigger deal. And I think there's enough workshops going on that I'm sure you could probably figure out. You can probably find a Intro to Python workshop, or if not, it's not a particularly hard language to learn, but it does require some getting used to, especially if you've done other languages. But I hope that gives a decent idea. Google Colab is pretty nice in terms of visualizing your work, though. But I have some additional searches here. But basically, do you need to click play in order? Yes. So, for instance, if you click one code segment that refers to another, like an object or something in another code segment, it's not going to know what you mean because it's not defined. So you do actually have to do it in order, yes. Though, if you go to the top, like there's a runtime and you can do a run all, it'll do them in order from top to bottom. But anywho, just going to go real quick. This is actually a graph created by this code right here. Basically what this did is it checked search depths at a kind of random move at a random position for alpha beta. And this is basically an idea of time. So you see for lower depths, especially 2, it just goes so quickly. It's like nearly instantaneously. But the higher you go, it definitely increases exponentially. Even by 6 or 7, it gets pretty high. This is in seconds. So depth of 7 will take almost a full minute to figure out a move. 8 gets even crazier. It's like 2.5 minutes. So it grows quite quickly. However, if I were to run it with just regular Minimax, which I'm not going to do because it'll take a while, it's going to, when it gets to depth of 6, it's going to have like a higher time than even that. Than even the 8 here. It's going to be like 3 or 4 minutes or something. So alpha beta really does have a dramatic effect. If you do want to see it yourself, I'd recommend running it. But if not, just take my word for it, or look at the internet. You can trust it for this at least. But I think that covers just about everything. Yeah, white one. So, do you all have any more additional questions about the code, about the concepts, about anything, even tangentially related? I'll give it another minute or two. In case you missed the link, here it is. What is the acceptance rate for AI mentoring? So that I can't answer. You would have to talk to. My best impression would be that you would have to actually go to the AIS Discord and ask someone there, because I personally am not experienced. Any resources where we can learn and practice this more? So honestly, there's just kind of a lot of resources everywhere. It's not like it's a pretty well documented thing just in a lot of areas. So I don't have any particular resources, but if you looked up alpha beta pruning or transposition table or something like that, you're almost guaranteed to find something. Mainly in the context of chess, that's pretty common. Is there a sign-in link to show we intended? That's actually a great point. Do we have something? Hold on for a second. I'll get to that in a minute. In terms of resources, there's a lot of space for that. Oh, I'm sorry. I'll get to the sign in a bit. I know you guys want to sign in so you can get that set up. And we're figuring that out right now. Sorry, this is the first one of the semester, so this wasn't quite set up 100% correct. We'll have the sign in link ready though. So, yeah. Today's event is a freebie. All right. Well, this event's going to be a freebie. So that answers that question. Any additional questions for you all? All right, I'll give it 5, 4, 3, 2, 1. Okay. Oh, enough for me. Thank you. All right. Well, I appreciate you all for coming. Hopefully, you all learned something from this. If you have any issues with any of the content in terms of understanding, you can always go back and go through the presentation again. And if you still have any questions, there's a lot of resources online. Or you could also contact someone from the Discord in AIS. They'd be happy to help you. I'm on there as well. Thank you for listening. Well, thank you. In that case, I'm going to be going offline. It's been awesome talking to you guys. Thank you.